Hi everybody, this is Mr. Zarzak, and in this screencast I'll be addressing general problem-solving approaches involving applying the law of conservation of momentum. So let's get right to it. First, let's take a look at an elastic collision problem. Now granted, this one has a heading and it says right at the top, inelastic collision example, all right, but when we see these in class, whether it's on WebAssign or assessments, okay, it's not going to be spelled out that it's an inelastic collision. We're going to have to determine it, all right? And so the key is to read the problem carefully. So it says here, radioactive man, 200 kilograms, flying towards a cannon at 25 meters per second, catches the 10-kilogram cannonball, traveling at 400 meters per second. What is the resulting speed and direction? All right, the key word here is that radioactive man catches the cannonball, okay? That means that after this midair collision, the two objects are going to move together. All right, so then the next step is I'm going to go through and I'm going to identify my knowns and figure out what it is I'm being asked to solve for. So I see here I'm given the mass of radioactive man as 200 kilograms. Okay, so I'm going to make that my first mass, so that's M1 equals 200 kilograms. All right, and let's see here. He's flying towards the cannon at 25 meters per second. Okay, so that right there, that's going to be his initial velocity. So we're going to call that V1, and that's 25 meters per second. All right, and so here he catches the 10-kilogram cannonball. Okay, so that's my second mass. So I'm going to label that as M2, and that's 10 kilograms. All right, traveling at 400 meters per second. All right, and so let's see here. So V2 equals 400 meters per second. Now, this is one of the most important parts of the problem here, is that if I look at my information, specifically the speed of radioactive man and the speed of the cannonball, I can see that the speed of the cannonball is greater. So the only way that radioactive man is going to be able to catch this cannonball is if the two objects are going in opposite directions. Okay, so it doesn't really specify which way is which. All right, so I'm gonna make the decision. All right, I'm going to make radioactive man traveling to the left and the cannonball traveling to the right. All right, and I'm going to make the choice here that I'm going to make my positive direction to the right. As a result, okay, one of these two velocities needs to be negative. Since the cannonball is to the right and radioactive man is to the left, that makes radioactive man have the negative velocity. Remember that velocity is a vector, all right, and so direction makes a difference. Now, like in most cases with physics, a little sketch can really come in handy. So I'm going to go ahead and make a quick sketch of what's going on here. So I've got my cannonball, and that's initially going to the right. All right, and then I've got radioactive man here, and I'm not much of a drawer, but that's okay. I'm just going to make a little stick figure. So there's radioactive man flying along to the left. Okay, and then I'll really come in handy later on. Now again, this is an inelastic collision problem, all right, but I'm going to start by writing the general form for conservation of momentum. All right, the equation says M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime, with those little primes just signifying after. Okay, it's going to help me keep track. All right, so now I'm going to go through and plug in for my knowns and solve for my unknowns. Oh, one more thing real quick though. Since I have identified that this is an inelastic collision, okay, it's going to work out that these two velocities afterwards are going to be a shared velocity. So I can save myself a little trouble, all right, by going and rearranging this equation just a little bit. And so what I'm going to do here is I'll just rewrite this as M1 V1 plus M2 V2 equals the sum of M1 plus M2 times V prime, where V prime is just their shared velocity after this collision. All right, so now if I need to, I can sneak back up here and take a peek at my given information. Radioactive man 200, V1 negative 25, M2 10, and V2 400. Okay, so let's plug in for what we know and solve for what we don't. Radioactive man 100 kilograms. He's going along here at negative 25 meters per second. Again, that means to the left. To this, I'm going to add this to the cannonball, which has a mass of 10 kilograms. Is going along at 400 meters per second. There's my before. I'm going to set that equal to after, which is the two masses together. Oops, let's make that in, let's stick with our blue here. All right, I got my two masses, 100 radioactive man, and 10 for the cannonball. And together they move along at some unknown speed. All right, so for radioactive man here, he's got a moving inertia or momentum before, that's negative 5,000. And then for the cannonball here, cannonball's got a momentum of positive 4,000. All right, and then together they've got a combined mass of 110 kilograms, and they're going to move together after. All right. Now, before I go any farther, okay, I'm going to scroll back up to the picture just to kind of make a point. All right, the cannonball here has a momentum of 4,000, and that's going to the right, whereas radioactive man's got this 5,000 to the left. All right, and so the important thing here is that radioactive man has more moving inertia than the cannon, and I'm sure you can see here pretty quick that he's got more by 1,000. And so what that means for us afterwards is that, well, since there's more moving inertia to the left before the collision, there's going to be that same moving inertia to the left afterwards. In other words, when we solve for this velocity, we should expect to get a negative number. All right, so let's go ahead and finish the problem and see if it works out. All right, so jumping back down here, I see that I wind up with negative 1,000, which is the sum of adding negative 5,000 and positive 4,000, equals 110 times v prime. And then my last step is to divide out that 110. So that cancels. And go to my calculator, and I'll find a negative 4.76 as my answer. And since that is the value of the cannonball and radioactive man afterwards, units for velocity is meters per second. And that negative sign just means exactly what we expected, which means that the two of them will move to the left. The negative sign shows me the direction, okay, whereas that right there, the scalar part of velocity, that's the speed. All right, next up we'll do elastic collision. All right, now in this example we're going to look at the same basic problem just as the example of the elastic collision. All right, so just taking a quick read through, it says a cannonball hits radioactive man 200 kilograms from behind while he's flying at 25 meters per second, and it bounces off his head. The cannonball's 10 kilograms, was traveling at 400 meters per second. Radioactive man's velocity is increased to 50 meters per second. What is the speed of the cannonball and its direction? Okay, so key word that shows us elastic, okay, because again, this has a heading of elastic collision example, all right, but come web assign or test time, we're not going to have that to guide us. We're going to have to figure it out, okay? Keyword, bounces. That's our indicator that we're talking about an elastic collision. All right, we've got similar initial conditions as before. So here we got radioactive man, 200 kilograms, so he's going to be our M1. Okay, and I'm still going to take the time to write all this out because it's going to save me some trouble later on and keep my thoughts organized. He's hit from behind while he's flying at 25 meters per second. All right, so I'm just going to write that as 25 meters per second. I'll figure out direction here in just a minute. All right, and it bounces off the head, off his head. Okay, so now we've got information about the cannonball. So 10 kilograms from the cannonball. So M2 equals 10 kilograms. It says it was traveling at 400 meters per second. Okay, note the past tense there. So that's my indication that this is this initial velocity of the cannonball. Okay, and again, we'll figure out direction here in just a second. All right, so it says radioactive man's velocity is increased to 50 meters per second. All right, so there's nothing to indicate a direction change here. All right, so my V1 prime is going to be this 50 meters per second. See, from 25 to 50 meters per second. And it says, what is the speed of the cannonball and its direction? All right, and so really the only unknown here is going to be this v2 prime, and that's what we're trying to figure out. So I'll put a question mark by that. Let's try that one more time, huh? A question mark. There we go. Okay, so it says right here, radioactive man is hit from behind. Okay, and if we look at the speeds, radioactive man 25, cannonball 400, okay, that would seem to indicate, all right, that both radioactive man and the cannonball are moving in the same direction to begin with, right? And so if I just go ahead and, again, just a quick little sketch can really save us a lot of time. I'm going to stay with positive to the right here, okay, and see what we got here is we got radioactive man, and he's going along this way. All right, but see, the cannonball is going to come in from behind, catch up to him, and hit him in the head. All right, now what happens afterwards, we're not sure yet. I mean, that's what we need to figure out. We know that radioactive man winds up having his speed actually increased by the cannonball. Okay, so our job is to figure out what happens to the cannonball itself. All right, so scrolling on down here, I'm going to start just like before with that conservation of momentum equation. So I got m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. All right, now unlike with the inelastic case, all right, this is the general form. I'm going to have to stay with this because both radioactive man and the cannonball are separate before and after the collision. The only time they're in contact is during the collision. All right, so let's go ahead and sub in for our given information. All right, so radioactive man, 200 kilograms, flying along here at 25 meters per second. All right, and then we've got the cannonball, which has that mass of 10 kilograms. 10 kilograms, going along at 400 meters per second. 400 meters per second. All right, so those are before. I'm going to set that equal to the after. All right, so we've got information on radioactive man. Radioactive man still 200 kilograms. 200 kg. Speed is increased to 50 meters per second. All right, whereas the 10 kilogram cannonball, 10 kilogram cannonball, okay, we don't know what happens to it afterwards. So V2 prime, there's our unknown. All right, so from here, all we need to do is do a little math. 200 times 25 is 5,000. Plus, let's see, 10 times 400, that is 4,000. Then afterwards, we've got 200 times 50, that's 10,000. You can see there, that's radioactive man's momentum increases. All right, plus mass of the cannonball, 10, times its velocity, after. Just going to give myself a little more space here. Okay, so adding these up, I wind up with 9,000 as my momentum before equals 10,000 plus 10 V2 prime. All right, so first step, I need to subtract out that 10,000 from both sides of my equation. I wind up with negative 1,000 is equal to 10 V2 prime. And last step is just divide out that 10. And we're left with our final answer, which is the cannonball bounces off at negative 100 meters per second. V2 prime. And just again, okay, the negative sign tells me the direction, so that's going to bounce to the left. And the 100 part, that is the speed of the cannonball. It kind of looks like a smiley face too, doesn't it? All right, next problem. All right, now let's look at impulse, starting with radioactive man. Okay, notice I brought over the given information, all right, from the problem along with the speed of the cannonball that we solved for after. Okay, remember that impulse is the change in momentum, and we've got a couple different ways that we can solve this. Okay, we can go impulse is the product of force times time, or we can also look at impulse is equal to mass times the change in velocity. And in this case, because we don't know anything about force or time, all right, impulse is mass times change in velocity is going to be the way to go. All right, so since we're talking about radioactive man, all right, these get the subscript 1. And if I expand this out, all right, if you remember the general format when we got that delta, the little triangle for change in, is always going to be final minus initial. So it says VF minus VI. All right, radioactive man has a mass of 200 kilograms. All right, his speed is increased up to 50 meters per second. All right, when it was 25 meters per second. And so if I go through and do quick calculation, all right, I wind up with a 5,000. Okay, and if I look at my units, kg m over s. Okay, and the last little thing I want to show you just real quick here is that when we talk about impulse, we'll write these units of kg m over s a little bit different. Okay, we're going to write an equivalent unit, 5,000 n times s. All right, that's Newton's time seconds. Now, I'm not going to go into this really deep. You can figure out for yourself that these are equivalent units, all right? But that's really just to make the distinction between momentum and change in momentum. All right, now, when we look at the next problem, you might see why we're doing these calculations. All right, we looked at radioactive man. Now let's look at the impulse of the cannonball. Okay, now again, I've always got these options of either impulse is force times time, that's where that Newton's times second unit comes from, or impulse is equal to mass times the change in velocity. All right, since I know the mass and I know both velocities for the cannonball, it's going to be much easier to apply it like this. All right, so writing it out one more time, impulse is equal to m2 for the cannonball times the final velocity, which we call v2 prime, minus the initial velocity, which is just called v2. Okay, so I'm just showing you a couple different notations here. All right, so I got 10 kilograms times that final velocity, negative 100 meters per second, minus that initial velocity of 400 meters per second. Okay, so here's the tricky part, is that in this, we've got a negative value subtracting a positive value. So what you're really going to do here is you wind up adding these two negative values, and you wind up with a negative 500 inside the parentheses. And so when I go and I take and I multiply that by the mass of the cannonball, you actually see that I got an impulse or a change in momentum of the cannonball of 5,000. I'm going to use those units of impulse as Newton's times second. Okay, when we look at the last question, I think you'll understand why. The last question, it says, what's the net change in momentum of the system? So when I talk about net, that just means total. All right, and so to get that total, all I need to do is sum up the two impulses. Radioactive man was number 1, and the cannonball was number 2. And when I first put in these numbers, it might be surprising. Radioactive man had an impulse of 5,000 Newton seconds, whereas the cannonball had an impulse of negative 5,000 Newton seconds. Changes in momentum that occur in the opposite direction. And so the net impulse or change in momentum winds up being 0 newtons per second. Okay, so now take a moment and think about what that means. Are you ready? What that solution means is that the total momentum of the cannonball radioactive man system does not change because momentum is conserved. the total momentum before the collision must be equal to the total momentum after the collision. That concludes our screencast. Thank you for watching.